Our next presenter is Javier Abud. Javier is coming from Denmark.
Yeah, that's where I live. I'm from Mexico originally.
Although your name doesn't look Danish, yeah?
No, not that Danish. No.
And he works at Unity, and he is going to talk about log-free, yeah?
Yeah,
So go ahead, Javier. Thank you.
thanks. Hi, thanks for coming to my talk. It's a quick one. So I'm going to be talking about a practical example of how I use log-free queues to do something. Little overview about the talk. Going to be a little bit about me. Then we'll talk about some existing log-free queues that are out there. Not that many, at least not in the public. Then a practical example of parallelizing code, and finally, just a little summary. So, who am I? Well, I started making games back in 2004 in a studio in Kuala Lumpur. So I have had the chance to travel a little bit while making games. I've made games for Nintendo DS, Flash, a bunch of other places. And all of them have had some sort of challenges, it's always a good learning experience. I'm currently working at Unity as part of the asset database team. So this team looks at whenever there's a change in your project, what things need to be re-imported. If you have a model and you change the texture, perhaps you need to re-import that, maybe not. So we deal a lot with dependencies and with assets in your project. So anytime you Alt and Tab into Unity, that's essentially the code that my team is running, or the team that I work with is running. So, but enough about me. Let's talk about these log-free queues. Of course, I looked it up on Wikipedia, but I thought maybe I should provide my own interpretation of it, where it's a thread-safe data structure that you can add elements to without using mutexes or locks or other sorts of semaphores like that. And the threads should not stop. And other threads should not be stopped because when accessing this. So Moody Camel, he does this by having an atomic counter, knowing where the head and the tail of this is, and uses that to figure out where to write data to next, and also to give an approximate size. Now then, there are existing queues out there. We have Boost. It has its own log-free queue, and it has a very nice description on the website as well. There's also Intel's threading building blocks queue, concurrent queue. And the one I'll be talking about today is Moody Camel's concurrent queue. So the one of the advantages that it has is that it's a single header file implementation. So I don't need to pull in a framework, and I don't need to have a large dependency on additional code. Like I said, it uses atomics when queuing, dequeuing, and estimating the size. And to reduce contention between the queues, it uses many internal queues to handle to reduce data sharing. How would somebody use it? And I hope the size is okay. If you you declare it, and then you start enqueuing things into it. So this is a very basic example where I give it a path of some documents, and I give it another path, and you can add whatever number of paths. And then what we want to do is, when there's many threads, you want to extract some data from it inside the threads themselves. So you have you create your thread, and then you extract that information within your thread. And you do whatever you need to do with that data. In this case, I would parse it and extract the word counts. But already you can see there's no locking here. It's just you queued some data in, and inside the threads, you're just taking it out as requested. And then you just wait for them to all execute at the end. The basic API is when you just queue and you try to dequeue. There's a little bit better API where you can bulk the operations as well. And finally, there's a more advanced API, which I won't really be getting into in this talk, but you can essentially provide a token that says, I want to be more specific as to which data that I will be getting back. This is per producer. So let's see if we can parallelize some code in practice. And the performance problem I want to highlight, or that brought me to using a Moody Camel, is that I started using NeoVim at one point, and it was using the Telescope plugin, and it was great for smaller repos. I was able to find files, search in files quickly, but on larger repos, it was actually quite slow. And what to do? Well, first profile, and then we decide what to do. So using Superluminal, it's a Windows profiler. It's a sampling profiler as well. You can see that this thing is taking 15 seconds doing something. If we look underneath a little bit, it's calling things like find next file, find first file, and it seems to be doing that over and over again. Now, this is typical of directory enumeration. You have a folder, and then you start adding it to a list, right? And then you go through it and you say, give me the file. Then, I found a folder. I need to recurse into it. Add the file that's in there, get the next file if there's one available, and then jump back, or pop the stack back. Then you move forward, and that's all the files you get. It's a very common pattern to follow. If you search for code examples, there's a ton of implementations of it doing the exact same thing that I'm showing you here, where you get the first file, then you say if it's a directory, and it's not the dot or 2 dots directory, you add it to this particular list, and you go back in, and you go as far down as you need to, and then you come back up until there are no more files left. So this is a pretty well followed and established pattern. And yeah, and then we got to close the handle as well that we opened with a find first file. So for Chromium, as of a couple weeks ago, it had 509,000 files, and it took 15 seconds to go down and enumerate the entirety of it. LLVM, on Windows at least, it took 8.2 seconds to recursively enumerate. So the question here being is, can we go faster than 15.3 seconds? And we look at the profiler, and it actually annotates where the time is being spent. And you can see that there are two things that are taking up 90% of the time, which is find next file and find first file. These are functions that are supplied by Windows, so there's not really much we can do there. And the rest is 10%. And we could spend quite a bit of time trying to optimize this 10%, but it's really not, it's not that amazing to get a 10% speed up. So we can have an opportunity in parallelizing this particular code. But before we get into that, I want to talk about some tools of the trade. There's everything from void tools. If you're ever trying to find a file on your machine, everything is incredibly fast at finding it, provided that it has synced the journal. There's, of course, fsmonitor for Git. You start it up on a particular folder, and it will tell you when there's a change on the folder. And both of these require a running service, and as many of you probably know, that is additional maintenance. So not only do you have your code base, now you have a service that needs to interact with it. So that's maybe not desired. And there's also overlap, right? One of them uses a synchronization point to say, I have an up-to-date view of your hard drive. And the other one says, these are the things that changed. And generally, it's only a few things that change. It's not the entire folder structure. So we look at the parallel directory enumeration approach. It is brute force, but as hopefully I can show you, it's also quite fast. And just to keep it simple, I'm ignoring symlinks for the sake of this, because that would just kill the performance in terms of trying to figure out if we already visited one of the nodes as well. All right. So how do we parallelize it? So every directory, it can have files, and it can have other directories, and so on, down the line. And the other restriction is that the approach should be general. So we can't know the folder structure up front, so we can try and enumerate whatever path you point the tool towards. So given these restrictions, we can say, what if once we find a directory, instead of recursing into it, we add it to a shared queue? And this is a multi-producer, multi-consumer approach, where each thread produces or queues up the discovered folders, and at the same time, the thread also consumes the folders and starts enumerating them. It becomes self-balancing because we are adding one, and then we continue operating on the existing data, while some other thread takes that and potentially appends to the existing list. So how does this actually look in practice? I have some pseudocode, and then I have the actual implementation. So we need to give it a root folder, right? We need to say, I want to enumerate this folder. And while there are threads running, or the queue has some entries in it, we dequeue, write the next entry. We use our good friend find first file, and there are, while entries remain, we keep iterating, just like in the recursive approach, except that when a folder is found, we are going to enqueue it in a shared queue rather than recursing. And so this is what it looks like. We check that we have running threads, or the size is not empty, or the queue is not empty. We then take an element from this list. We get the handle to the first file in that folder. We fill up find file data, and while there are files left, we keep iterating. As soon as we find a folder, we do two things. One is we copy the path to the outgoing list, and the second thing is we enqueue the path that you just found, which is a directory. And this is the queue that the other threads will be looking into to find out if there's more information or more directories to recurse into, to enumerate. So before it was taking 15 seconds. With this approach, it takes 2 seconds to enumerate Chromium source. So that's not a 10% speed up, it's a 6x, 6.7. Same with LLVM, we were at 8 seconds, now we are below 1 second to enumerate all of it, right? So that's a pretty nice optimization, and it generally uses all the, like there's no undefined state. Like you are getting the folders, and you're not taking any shortcuts to get them. You're essentially converting a recursive algorithm into a parallel algorithm. If we take a step back to think about what are some of the problems that this can help tackle, if you look at a folder structure, you can think of every directory as a node with potentially some neighbors. Maybe it doesn't have neighbors, maybe the folder's empty. But either way, this is one, you can get some neighbors from it. And then every file is essentially a node with no neighbors, which translated to a diagram, you have your node, you have some other nodes, and essentially it becomes parallel graph traversal. So some possible applications: you can traverse a social network graph quite quickly. You can also crawl a website as well. You can get some links inside that site and start expanding it recursively, in parallel, sorry. Task scheduler as well. You have a number of units of code that you would like to run. You can start saying like, I want to run this and that and that. And thinking about it a little bit, you can even parallelize breadth first search and depth first search, provided there's no cycles in it. And there's probably other applications. And in general, the template for this can look like that. It is essentially this. You have a counter of how many threads are running. You do the dequeuing. You check things are not complete. And you can put your code in the middle to do whatever you would like to do. So now the question is, can we go faster than 6.2x? So we already had a nice win, but let's see if we can go further. There are some Windows internal functions, like nt query directory file and others. And of course, a big caveat is that if you have an antivirus program, it will quarantine and delete this code. So just be aware. Or have an exclusion rule for it. Find first file calls nt-query directory anyways. With the sampling profiler, we could see this. It just does it down there. So it does technically work. And to get the function pointer from it, again, this is all Windows stuff, but it's still quite prevalent, right? Like, it's very common to just wait for things to be enumerated. You get the handle to the module, and then you get the process address, and then you get the function pointer from that, and then you just call it in with the right arguments that you have to also define ahead of time. And this thing, it actually speeds up even more. So now we're at 11 times the speed of the original implementation. So from 15 seconds down to 1.3 seconds. LLVM, it's at 18. Other large repos can potentially use this as well. Use this speed up too. And can we go faster than 11.3x? Generally, I would say yeah. We can always keep optimizing away, right? It is a race to the bottom. Like, how fast can you actually make this thing go? And some ideas, well, of course, you would have to profile to see what's going on. You may want to use the producer tokens as well, so you can be a little bit more specific and reduce some of the possible contention. And again, if you can profile, then that would be my recommendation. In summary, if I don't sound like a broken jukebox, profile first. And because it is quite tempting to guess what could be optimized. You saw in the first example that it was a potential 10% speed up if we fixed all the minor issues there. But 10% is not 6x or 11x. Look at the particular data structures that are out there. This one seemed to have, so Moody Camel's implementation seemed to have addressed this issue. Perhaps there are other data structures out there that are even better suited to this problem. We could also do it using locks, but the speed up may not be quite as dramatic, as we would still have to be waiting on the other mutexes to exit. And if anybody knows about a concurrent hash set, then we could even handle the symlinks and the cycles in a graph. And of course, with a sampling profiler, we can look under the hood and see if there's some additional tweaks that we can get by looking at some of the underlying systems. I've put the code available on GitHub. I've also gone ahead and added a QR code in case anybody wants to check it out. It's there, it's available. You can run your own benchmarks. You can even try and make it work for other platforms like Linux or Windows or Mac. It may not be, the contrast may not be as large, but still, it would be a fun thing to try out. And with that, I just want to say thanks.
Thank you very much. Questions? Oh.
Hello, thank you for the talk and the numbers and the statistics.
Thanks.
One question I had is, so you showed the advantage of making use of the idle spare CPU that you have in your computer. What I would be curious is to see on a single core CPU, for example, how did perform the original unoptimized code, and after the parallelization, how much is still that number of seconds that it takes to iterate over all the files? Like if you don't have chance to parallelize, let's say, in your system, how much has it been the penalty of the extra overhead that you introduced to be able to parallelize?
Yeah, so that's always the trade-off, right? You introduce something that's a little bit more complex for the sake of a larger set of data, or to go through a larger set of data. So for a smaller repo, it may be comparable in speed, but the real difference here is how much the larger repositories benefit from this. But in terms of time, I don't have that data.
Thank you.
By the way, how many cores did you have in that machine?
How many what?
How many CPU cores did you have available in the machine where you made the test?
Oh, yeah, this is my own machine at home. It's got 12 cores.
12 cores, okay, thank you. Any other question? When I ask any other question, there is always somebody in the other end of the room.
So I'm curious about the performance if instead of using a log-free queue, you use just a normal queue with some mutexes and some things like that, because I'm guessing that the vast majority of time you are spending in doing I/O. Does it matter that much to use a log-free queue here, or do you know?
I think for the sake of the simplicity of it, that's the real takeaway. We can throw a mutex in there, and we can say, now I'm going to add something to this queue, and then let the mutex go away. But I wouldn't be able to tell you if there is that much of a difference.
So you mean that you wanted to use the implementation, but if you have another implementation that under the hood uses mutexes or something like that, it is going to be almost the same in terms of performance?
I guess it may be comparable, because you're right. You pointed out most of the time is spent trying to get the data that says this what is in this folder. Because like find first file actually allocates a buffer. So it's the OS saying like, okay, give me that buffer, and then like if you look at it with process monitor, it will actually not do any more system calls until you say, I want another find first file. Find next file does not produce system calls. But yes, like most of the time is spent getting data from the OS.
Thank you.
Okay, thank you. More questions? Okay, thank you very much.
Thank you.